Tonight I have some fairy lights that I got from Kmart here in Australia on special for about $6, and they're quite nice. They are what they called their Moroccan style, and they were clearing them out, so I bought some, and tonight's experiment is to see whether these lights can be controlled by the ESP8266 Wi-Fi Internet of Things device. So tonight is all about the Internet of Fairy Lights. Okay, so here are my fairy lights with an IP address, and if I use my mobile phone here, and this is a little bit of software called my MQTT, just a useful tool to send a MQTT message or to receive them as they come through. If I send the message to turn my fairy lights on they come, and they look just beautiful here. You can see the nice patterns that are created by these Moroccan style fairy lights. Really like them a lot, and nice reflection as well. So, and if I hit them up with another message through MQTT to tell them to turn off, off they go instantaneously. Back on again, back off again, back on again, back off again. So completely wireless communication with these fairy lights, and lots of neat applications for this. So of course control from smartphone is kind of neat, but the other thing that can happen is you can set up a cron job that just sends out a MQTT message at the right time of the day, and your fairy lights will turn on, for instance, at dusk, and then turn off at, say, 10 p.m. And of course, you know, taking it a little bit further, you could have different modes for when you're on holidays and when you're at home, different modes for weeknights and weekends, and so on and so forth. So you get lots of flexibility in terms of turning on your fairy lights by giving them an IP address. And the way that they've got an IP address is this little ESP8266 module here, and a MOSFET and a transistor here to control this string of fairy lights. What I'd ultimately like to do is to control a much larger set of fairy lights, but this is a little breadboarded experiment, and it's worked out quite nicely. So stay tuned, because in the next part of this video I'm going to talk about in more detail how I made these things work. But for the moment, I'm going to switch them on and switch them off, switch them on and switch them off wirelessly through my Wi-Fi router and MQTT. Yeah, good fun. I thought it'd be interesting to take a look at how much current these things draw when powered from their little solar control circuitry here and the single nickel metal hydride cell that will inevitably be within this box. And yeah, always struck by how little current these things seem to take. Here we're measuring about 4.5 milliamps using a multimeter inserted in series here to measure the current. So it's only about 450 microamps per LED, and yet they're still glowing quite brightly and pleasantly and casting nice patterns on the table and so on and so forth. So yeah, I mean, while you might typically think to run an LED at 10 or 20 milliamps, these guys are running quite adequately on microamps really. So here's the little box of electronics that was powering the solar lights. Thought it'd be interesting to see what's inside, and well, I stand corrected, it's a nickel cadmium battery, not a nickel metal hydride. Little switch in series from the battery to the circuit board, and yeah, then a teensy little circuit board here just dangling in free space, and connection to the solar panel on the back, and wires going out to the LEDs. Close-up view of the circuit board, and there's the little 4-pin chip that's really common in these solar garden lights here, and an inductor. And together they boost the 1.2 volts nominally from the nickel cadmium cell up to 3 volts or a bit more in order to light the LEDs and reach their 3 volt forward voltage. And provision on this circuit board for capacitors and all sorts of other, no doubt, useful components, but they've gone the minimalist route here and have nothing more than the 4-pin IC and an inductor. Nevertheless, it seems to work. Alright, so my objective is to power the string of 10 paralleled white LEDs here from GPIO 5 on the ESP8266. Now, when it's high, this is 3.3 volts, and because it's just a GPIO pin, it's not going to be capable of sourcing a substantial amount of current. While it's true that it might be able to send the 4.5 milliamps or so of current that we need here, you know, that might be pushing it for this device. I'm not quite certain, so the best thing is to put some buffering stages in here in order to ensure that only a minimal current is drawn from this GPIO5. The other thing is this GPIO5 is at 3.3 volts. If the forward voltage of my LEDs here is around about 3 volts for a white LED, you know, there's not much of a margin there, not a lot of headroom. So what I'll do instead is to run this off a 5 volt supply straight from a USB power supply. Now that leaves the question of what value this resistor should be, and if we're targeting 4.5 milliamps like when it was operating from the solar power supply, then what we want to do is to size the resistor such that 4.5 milliamps will flow through the LED. Now, because the LEDs are in series with the resistor, whatever current flows through the resistor is going to be the same as the current flowing through the LED. That being the case, what we can do is calculate the current that will flow through the resistor and size the resistor appropriately. And in order to do that, we need to subtract V plus from the voltage dropped by the LED. So that's just saying that if we've got V plus here and the voltage dropped by the LED, then the top part of this fraction will now represent the voltage across the resistor. So in this case we've got 5 volt supply voltage, about 3 volts dropped across a white LED, and at the bottom we've got the current that we're targeting. So in this case it's 0.0045 amps or 4.5 milliamps. And if we do that calculation, just basic Ohm's law here, we get 444 ohms would be the ideal resistor size. But of course resistors only come in standard sizes, and the one I had most ready to hand was a 470 ohm resistor. So that's what I'm using for R here, 470 ohms. The device I'm going to use to buffer the GPIO output is a P-channel MOSFET. This happens to be the FDN340P. I have a bunch of these on hand, and they're quite useful for low voltage, moderate current applications. They're a P-channel MOSFET and they're a logic level MOSFET. So you don't need a great voltage between the gate and the source in order to switch these on. It'll turn on pretty fully at quite a low voltage between the gate here and the source. So useful for interfacing directly with microcontrollers. And the way this thing works is that current will be permitted to flow from the source to the drain here, so from the 5 volt input here through to our LEDs when the gate here is pulled down low relative to the source. And when about 4.5 volts exists between these two, this MOSFET is really very much turned on. So when that happens, it looks like around about a 70 millivolt resistor or so, so it provides a pretty low resistance path from source to drain. Now when this thing is pulled high, so when the gate is effectively pulled up to match the source voltage, then this device is off, and it just looks like a switch or an open connection here. A very high resistance exists between the source and the drain, and the device is off. But therein lies a problem, because if we need to pull this gate right up to the source here, that's kind of impossible to do, because the maximum we can pull this GPIO pin up to is 3.3 volts. So if we tied this GPIO pin directly to this gate here, the maximum we could take it up to would be 3.3 volts. So there'd still be about 1.7 volts that existed between the source and the gate, and with that kind of voltage between the two, it's very likely that this kind of logic level MOSFET would still be conducting a little bit. So we wouldn't be able to switch it off completely. So what we need to do is to interpose another stage of buffering between the GPIO pin here and the MOSFET to ensure that we can fully turn the MOSFET on and fully turn the MOSFET off. So here's what I've come up with in terms of another stage. I've added a NPN bipolar junction transistor here. In this case I've got a 2N3904, pretty much a jelly bean small NPN transistor. And what happens is that the emitter is tied to ground here, and the collector is tied to the gate of the P-channel MOSFET, and also this 4.7K resistor. Now what happens is that if this device is switched on, it's like a short exists between the collector and the emitter. It's not quite a short, but in an ideal world it would be. And so what that does is effectively pull that gate all the way to ground. Now, as we said earlier, if more than about a couple of volts, and certainly by the time we reach 4.5 volts exists between the gate and the source, then this device turns on. So basically when this device is on, the gate is pulled to ground, about 5 volts exists between the gate and the source, and this device is on and current flows to the LEDs. Now when this device switches off, it looks like a really high resistance here, like an open circuit, and so this 4.7 kilo ohm resistor here acts to pull this gate up to 5 volts. And that way now basically 0 volts exists between the gate and the source, and so this MOSFET turns off, and turns off properly, and then a large resistance exists between the source and the drain, effectively switching off the LEDs by not allowing any current to flow from the supply rails here. Here what I've done is added a couple of resistors. So this first resistor here, which is also a 4.7K resistor, just limits the amount of current flowing through to the base here. So this base to emitter junction here looks like a diode, and it's a forward bias diode. So if we didn't have this resistor, what would happen is a large amount of current would flow from the GPIO pin through the base of the transistor and through to the emitter and ground this wouldn't do the transistor any good, and it would probably blow those that GPIO pin. So we put this current limiting resistor here of 4.7k, and then I've got another resistor here from the base to the ground, and that's a 47k resistor. The idea here is just to tie this base to ground so that it's in a known off position when this microcontroller is uninitialized. So it's common when a microcontroller is first starting up for its GPIO pins to be set as inputs, and so if we didn't have this resistor here, essentially what we'd be looking at is a base that wasn't really connected to anything here, and so any kind of spurious noise and interference could potentially start to turn on this resistor and start controlling these LEDs and switching them on and off and making them flicker or any other kind of nasties. And so if we tie this down, then we know that this is always in a known state. So it's a big enough resistor that the current coming out of the GPIO pin is always able to defeat it, but it's a small enough resistor that it ensures that this base is sufficiently tied to ground so that it doesn't waver around here when the GPIO pin is set as an input or is otherwise uninitialized. So there's a few more things to be said about this circuit. The first thing is that what I've got here is a Highside switch. Now this is quite advantageous because it allows your entire circuit to have a common ground. So if you're designing a PCB for this or something like that, it's often convenient for all the grounds on the circuit to be tied together, perhaps connected together by a copper pore or something on the PCB layout, and then to do switching on the Highside like this. So it's partially a convenience why I've gone for this this approach. The other thing is that I have a P-channel MOSFET on hand that was logic level and a good fit for this application. So Highside switching is what I opted for. The other nice thing about this approach, and that partially offsets the complexity of having two switching devices like this, is that a logic high here on the GPIO maps to current flowing here and the LED lighting. So there's no inversion of logic states or anything like that. So let's trace that through. So if you've got 3.3 volts here, then this transistor will switch on because there's current flowing from the base to the emitter. It'll switch on, and that will essentially short the collector to emitter. That will pull down the gate, and when 5 volts exists between the gate and the source, then the P-channel MOSFET will turn on. So there's no logic inversion, so that makes it quite straightforward, because whatever you've got in code writing out a logic high, it translates to the LEDs or whatever other load that you have here turning on. The other thing is that this circuit is really overkill for the application that I'm using at the moment. So I could have potentially just inserted the LEDs here and had the NPN BJT here turning those LEDs on and off directly. But I wanted to give this circuit a bit of a try because I'd like to switch some things that require larger currents here. So some low voltage amplifiers, maybe bigger strings of LEDs and that sort of thing. So that was part of the consideration for designing it this way. Now, in terms of component choices, as I say, this FDN340P was on hand. It's rated at about 20 volts or so, but the maximum voltage that it's specified in its absolute maximum ratings for the difference between gate to source voltage is 8 volts. So in this kind of application, if you were to increase the supply voltage to something like 8 volts, you're really kind of pushing it. So in many respects, this circuit is quite limited to switching, say, a 5 volt rail. So very much low voltage applications, but this thing could switch substantially higher currents than what I'm asking it to do here. So yeah, quite conceivable that it could switch an amp or two of current at 5 volts and drive quite a substantial load here. So I'd like to put that to the test sometime soon. As for other component choices, after working out the MOSFET here, I worked out the value of this resistor, and I worked it out so that about 1 milliamp of collector current would flow here. So basically we've got 5 volts here. Let's disregard the voltage that exists here when the transistor is switched on. That's referred to in the literature as the collector emitter saturation voltage, and I think in this case it's about 0.2 volts. But basically we've got 5 volts here. We've got a 4,700 ohm resistor here, and that means that about a milliamp will flow here through the collector. Now that's a generous amount of current to flow here, because the gate of a MOSFET is has an extremely high impedance. It basically presents no load here, so to have a milliamp or so of current here is really, plenty. But on the other hand, what's a milliamp, and particularly if this is being supplied from a wall wart or a plug pack, it's not a big deal. If you were to use this in a battery application, then you might want to think about a higher value resistor here. Now, why did I choose 4.7K here? Well, the idea was to provide enough base current, so current flowing here to the emitter from the base, enough base current in order to ensure that this transistor fully turns on for 1 milliamp of current flowing here. Now, this value here admits about 700 or so microamps. Actually, it's more like about 500 microamps or so. That's what the base current works out to be. That is more than enough to saturate this transistor and to allow 1 milliamp of current to flow. But it's well within the specifications of what this GPIO port will handle, so there's no great issue there. And also it has the advantage of being the same value component in both cases, so when you go and procure components you don't need to buy so many. So sometimes optimizing for less things on your bill of materials is a good approach too. This 47K resistor I just picked because it's about 10 times the value of this resistor, so it's not going to have a big influence within the circuit. So those were the design choices. As I say, if you were to build this for battery operation, then you might think more carefully about the choice of resistors because they will burn a certain amount of current whenever this thing is switched on. But in this case, and especially when I come to drive much larger LED strings that require a lot more current here, the current that's being drawn by this part of the circuit will become negligible in comparison.